Well, good morning. While they're loading up the presentation, I'd just like to say thank you for Professor Lee. It's been 28 years, and this year he actually celebrated his 30th year with our department, so quite an achievement, and he doesn't let up. He's always going. So I've also heard a few good things. First, we start off with some bad news. We are the worst in the infrastructure, and we've, as a bridge engineer, I've sort of been monitoring this. But the good news is we're there, so there's only one way to go up. And the other good news I heard is 2 people have already said they are hiring our students. So I see a lot of our students here. So get those resumes ready. Okay, so this morning I'm going to talk to you about an ongoing project that we've had. It's not complete, so I'm not ready to share any final results. But I will talk to you a little bit about what we've been doing. We spent the summer working with some students bridge testing. So we were looking at using ground penetrating radar to monitor bridge decks, concrete bridge decks, and trying to use non-destructive methods to evaluate what is actually going inside the concrete deck. So what is GPR? How does it work? How is it helpful? And what are we doing here in Rhode Island? So let me start off by saying GPR stands for ground penetrating radar. It is a high frequency electromagnetic reflection, and really the word ground here could be anything. You're looking at anything that's non-metallic, so you can look for soils, pavements, concrete. And it's not new technology, but they've been using it in geological sites, looking at soils, deep buried structures. And we can also extend it to looking for rebars, trying to locate rebars, look at the size of the rebars, the condition of the rebars, try to find locations and areas of deterioration and corrosion. And so this is what we have started to do here at URI. So how does it work? It basically measures a 2-way travel time of a signal, of a radar signal. So what you will do, it's like an echo. If you say hello down a shaft and wait until it comes back to you, so you're measuring how far it took for that reflection to come back. You can also look at the intensity of how it came back. So you can look at the amplitude of the signal and also how long. So that technology has been around for fish finder, sonar, and the like. So in terms of concrete decks, you have an antenna. It has a transmitter and a receiver. And it basically measures any time two different surfaces or 2 different materials will come in together. So it will have different properties when it travels through air, different from concrete, different from asphalt, different from steel. And so those reflections, those pings that we get back will try to help us locate and detect the type and the condition of these materials. The frequency of GPR that we use, generally it's transmitted in the microwave range. Our signals, we have a 1.6 gigahertz antenna, and that is the same signal generally in cell phones and 2-way radios, so we have to be careful we're out on the field that we don't get interference from such devices. In choosing the frequency, you have to be mindful of the resolution that you are after and also the penetration depth. So depending on where you want to capture your reflection, you choose the appropriate frequency. So in here, the resolution, here you have the transmitter and the receiver. The depth is one parameter that you need to be mindful of, but also resolution. How well can you identify or separate 2 closely spaced objects, so 2 targets? So it's a trade-off. So if you want to look deep into your specimen, you're going to go with a low frequency, low resolution radar. And if you want really high resolution, you're only going to be able to get shallow depths up to maybe 2 feet. And so we're sort of somewhere in the middle. You have to look at your application. We are concrete bridge decks. So we went for a 1.6, which gives us about an 18-inch depth, which is more than enough for us locating the bottom of the deck and also the rebars inside. So this just gives you an idea of what different appropriate applications. So if you're looking for geological profiling, if you want 90 feet, you can have a certain very low frequency We are about 18 inches, so a foot and a half. So what does a typical GPR scan look like? This is from a bridge deck. So as you travel, it will measure the distance of your profile. You lay out these lines, these travel lines that you're going to go across. So the x-axis here is distance, and the y-axis here could be time, which is the two-way travel time, or you can convert that into a depth estimate based on the properties of the material that you're getting. And these are the reflections. So this is the first reflection, these little parabolas here, hyperboles that you get. These are the reflections of your rebar. And explains down here, why does it have this cone shape? And the reason it has that is once you have your radar and it sends out the signal is sent out as a triangle, it's sent out as a cone in itself. And remember that it's measuring how long it takes for that signal to come back. And so if it takes a long time, it thinks that it's buried low, it's buried deep. If it takes a very short time, then it thinks it's on the surface. And so as it's traveling, if the antenna is not yet directly over the rebar, the signal that it comes back is this diagonal here. And so it's going to travel a long distance and then come back. So it thinks that it's low, and it puts it down here, the first point. As the antenna approaches the rebar or the target, the time or the distance that it would take for the reflection to come back will decrease, and then the radar thinks that the object is closer to the sensor. And so it continues to put these targets closer and closer until it's right over the target, and that would be the shortest distance for that, that radar signal to transmit and then be sent back. So what we do is you get these cone-shaped reflections, but we have to migrate them and we have to collapse it when we're trying to identify the actual rebar. So the actual rebar location is the top of the rebar. Different types of GPR systems. Rhode Island DOT currently owns an air-coupled system. This air-coupled, air-launched horn antenna, different words meaning the same thing. This is basically antenna that is mounted at the front of a vehicle, okay, of their truck, and it drives. You can drive this along the highway speeds, no disruption to traffic, and the signal is first sent through the air until it hits the pavement, travels through the pavement, the base and the subbase, and then is reflected back. So really good benefits from this is that there's no contact, safely operate at highway speeds, able to resolve thin layers. However, it's unshielded, so you do have interference. So if you're driving by a truck, you can get some interference. They're two-way radios. They're talking to you. It's not a completely clean signal. Applications, you can use this as evaluation of pavement layer thicknesses, so detection of anomalies in pavements, so really the health of pavements along a certain stretch of your roadway network. What can be done with this? This is from a project at Rutgers. I came from Rutgers, so I'm a New Jersey person, so I always like to see what they're doing. And this is the type of things you can extend this to. So we're collecting all this data. You can actually then say, I'm going to tag it to, as the truck is driving, you can put a video camera. It has GPS, so you can visually look at your infrastructure as you're collecting this data. So here is some video. This is the map and the GPS location, and it maps out the line that you are collecting the data. Here's your raw data, and it tells you again, the x-axis here is the distance, and the y-axis is the depth of your layer. So you have your asphalt, your base, and your subbase. If you take cores at any particular location, or as you're constructing around the state and you decide to take cores for a project, you can log that core into your database, and it would verify, it's one point of measurement that you would verify. So if you were to take cores, you can attach video, you can attach pictures and actual pavement depth. And the more you take cores and the more this database, you're collecting data for this database, you can start to verify a lot of these points and calibrate that way. So it becomes more of a network management, asset management tool. You can also use it for bridge decks. This is ground coupled, so the antenna is coupled to the ground. It is actually touching, it's in contact with the surface. You're able to, again, resolve thin layers. It is shielded with against interference. However, it's a slower process. You're actually walking this thing across the bridge. It becomes a little bit more accurate because you have a high resolution antenna. But what can you do with it? You can, again, locate your rebars. You can determine the concrete depth that you have. After you mill surfaces over and over, sometimes the concrete cover becomes low, and that makes your deck susceptible to infiltration from salts and environmental components. You can look at areas of deterioration. You can say, all right, for this entire deck, really how bad is it? Where do I need to replace the entire deck, or should I focus on maybe rehabbing a portion of the deck? So you can do some percentages. You can give it some sort of an overall rating. So this is an example of a bridge deterioration map. The red areas are really the highly deteriorated ones, and the blue are the low deterioration. So you can have an idea about what it is, your deck, without taking any cores. The system components is basically antenna that is housed at the bottom here in this white bucket. And there is the controller at the top. Okay, so it's as an internal memory. It has, it's water resistant, it's run on batteries. And you also have this thing called a DMI, a distance measuring instrument, and that is the one that is attached to your wheel here. And it measures the distance along your profile, and it will, it's calibrated, and it will tie your GPR scans to where you are along the bridge. So what have we been doing? We've been busy testing some bridge decks across the state. Our aim is to test 10 bridges. We're probably around 6 now. And we've worked with DOT to have them identify some bridges for us to test. So they're looking at, we want to look at really good ones, and we want to look at really poor ones. Okay, so we started off our first one in right behind URI here, Yagu Mill Pond. And I'm just going to show you pictures. I'm not going to share any results at this time, but just to give you an idea of what we've been doing. So this one here, this one was actually pretty good. It's relative, the pavement was really nice, so you can showcase that one. That's a good one. And it's really used by some heavy trucks, but not often. Very light volume. So it was rated, really good, so it's a nice one to start. The only problem is it was a really long bridge. This was our first one that we actually used during our training session with this equipment. But generally what we would do, and I'll go you through here, is that we would choose a lane and we would direct traffic. We worked with DOT on this, and we closed down a lane, and we would mark out a 2-foot by 2-foot grid across the lanes. And so here you see our students just with some spray paint. We'd mark these dots, we would dot it out as a grid, and we choose one profile, and we would take the GPR along the longitudinal profile. So this is probably the most time-consuming portion. We would do longitudinal, and in this case, we decided to do transverse as well. So we would do 2 feet every, 2-foot lines every 2 feet, and I think this was a 400-foot bridge, so it was quite time-consuming. The other ones we've done, we've tried to locate something near coast, so something near the water, something inland, something high volume, something low volume, something old, something new. And we tried to find different types of parameters that are bridges so it can tell us something about our data. So we also tested the Millgut Bridge in Colt State Park. This one was interesting. This one was rated as structurally deficient, and it was posted. So that was a different type of bridge, and we'd sort of do the same thing. Potawatomi Bridge over Hunch River in Warwick. That was probably the worst one that we did as yet far. It was short. It was a little bit isolated, so we didn't have a lot of heavy traffic. And that was one thing we did. Apponaug, we tested that one, and I should have brought it, but we had a screenshot of the traffic that we did. We went on our Google Maps, and it was all red dots, and we got cursed out, and it was, it wasn't the right location. And so we learned our lesson after that, and so we decided to look at low volume bridges, low volume locations. So that one had a lot of deterioration. When we swept this bridge, you can actually see the rebar. So that was on the far end in terms of deterioration. So that was a good one for us to test as well. Singleton Bridge in Woonsocket. We did this one this summer. That one had some scaling. This was a good candidate for us as well because it wasn't a nice clean one. We did Laurel Ave. That one was a nice brand new bridge. So that one, I didn't include it here, but that was the good one to give us a baseline. And we also did a ramp BB in North Kingstown. This one we were able to take some cores, and anytime we're able to take cores to validate our data, we requested that from DOT, so they were able to allow us to take some cores. Okay. So with that, so it is ongoing research. There is a student, Kelly Warren, and I think she appears in the afternoon on your schedule here that she can talk more about this. She's also looking at surface roughness, bridge deck roughness, and how that relates to deterioration. So this is all tied into the same project. So we hope to wrap up this project in the next few months. I would like to thank, obviously, DOT and the URI TC for funding this research. And I'd also like to thank there's a few students here that interned for DOT that also helped us. So, so thank you to them.